So we are very excited today to host Alexandre Gramfort for this episode of the CSML seminar. Alexandre Gramfort is a research scientist right now at INRIA, which is a French research center in the parietal team. His work is on statistical machine learning, signal and image processing, optimization, scientific computing, and software engineering with primary application in brain functional imaging, magnetoencephalographic data, electroencephalographic data, and functional magnetic resonance imaging. And before joining INRIA, Alex was an assistant professor at Telecom Paris-Tech. And before that, he was in Harvard University. Alexandre, in this talk, is going to talk about his research works in general. That includes leveraging information in EEG and fMRI data, both for natural language processing, independent component analysis, and self-supervised learning. With that, I'll leave the stage to you, Alex.
Thank you very much, Pierre, for the intro, and thank you very much globally for the invitation and for attending to this presentation. So I will share my screen. And so just as a quick intro from my side, I was not completely certain about the audience, so I tried to cover a broad scope of what my team is currently working on, really at the interface between ML and statistics and neuroscience or neuroimaging in general. So feel free to ask me questions during the talk, interrupt me if there's anything unclear. And I've planned 2 hours for this event, so I will not talk for 2 hours, but if you want to stay afterwards and ask me questions, don't hesitate. All right, so let's get started, maybe to give a bit of, let's say, broad context about what I'm working on. So for those of you who have never seen this picture, this is the brain of a patient from Paul Broca, was a French neuroscientist. And this patient was called Monsieur Le Borgne, was also known as Stan, which is the nickname of this patient. And the reason is because this patient could only say Tan, which is the only word that he could pronounce. And this is how basically Paul Broca understood that this part of the brain here is involved in language production, and basically mapped Broca's area into this region of the brain. So this obviously a big lesion in the brain. So this is really from an historical perspective, but now if you look at how people collect brain signals and how do they measure the living human brain, I'll focus mostly on like human signals, not really rodents or animals or like signal unit or multi-units. This is really not the type of data I work with. But let's say brain signals from humans, and what you see on the left is EEG signals that you see here, or a magnetoencephalographic signal that measures the magnetic field, or here an MRI scanner at 3 Tesla, or for invasive recording that you can do on humans for patients, for typically epileptic patients. At the end of the day, what you get is a bunch of multivariate time series from which you need to make sense. So if you look also now what's going on these days about these types of technologies, there's a lot more ways of observing the living brain, and maybe somehow to help us bridge the gap between, I would say, intelligence in the human sense and AI. And what you see here is a state-of-the-art MEG system. Here's a new device that is not available on the market that you can find online and social networks that also explain how these types of technologies work. And also cheaper ways, which are EEG, that you can have like consumer-grade EEG that you can collect at home, or like novel super high-field MRI scanners that you see at the bottom that now exist at Neurospin in the Sèvres in France. So at the end of the day, you get these signals, and you may ask yourself, okay, what can I do with these signals? And I guess at the interface between neuroscience and AI/ML, you can ask the question in both ways, which is, what can machine learning can do to make sense of these types of neuroscience signals? Can it help in a clinical context? Is it allowing us to answer new cognitive neuroscience questions? But also in the opposite direction, which is, can you see how the brain works to maybe inspire or see where ML systems are kind of failing and see how they can be improved? So to start to answer these questions, you can do a bit of statistics, which is really counting and see what people do with machine learning with on these types of signals, what types of questions that people study. And so what you see in this meta-analysis that we published a few years ago, people start to use machine learning and especially deep learning on the various types of applications, brain-computer interfaces, epilepsy prediction, seizure detection, but also on topics that we'll cover a bit later, which is monitoring and predicting things on sleep recordings. So example, also historical example that you can find, maybe have been kind of milestones over the last years, is really statistics or ML or signal processing, allowing to go from this brain signal that are collected on the motor cortex of this paralyzed patient and controlling a robotic arm. So this would be one way of using some kind of control system or ML system to read out from the brain and control a device. This is one way of addressing the problem. And one other way, maybe kind of going more from ML to kind of make sense of neuroscience data and seeing things in the brain that would be of interest for cognitive neuroscience. This is some work that we've done in the team many years ago, where we try to, I mean, that's been done many times over the years, and I'll come back to this later in the context of NLP task. But what we did at that time, using during the PhD work of Michael Eikenberry, was to kind of relate the activations of a CNN. So it was the CNN, pre-trained CNN that was called Overfeed by Pierre Samanet from many years ago, where we mapped each of the activations from the deep net to different voxels in the brain using fMRI, and showing things like these types of image where the color that you see here suggests that these low-level activations are a better features to predict the activation here in this part of the brain, whereas the high-level part of the activation of the deep net are more relevant for these extratriate regions. And so this is kind of a way to statistically map or correlate neural nets and how brain activates. Okay, so the first work I would like to highlight in this presentation is the work done by Hubert Banville during his PhD with me and over the last few years, which is how to leverage ideas of self-supervised learning to make sense of EEG signals. So why do we need to do this? What's the point? So the first thing I would like to highlight is that ultimately what we're trying to do is to learn representations of the data. What you see here is a short time Fourier transform of a speech signal. And you look at the speech signals, not at the raw waveform, but you look at it through a spectrogram. And that at least makes more sense to your eyes, and that you can basically eyeball. But this also applies to images with wavelets, but also in the context of neuroimaging, people have used these types of representations to look and to make sense of diffusion MRI signals. And the gist of this is that once you have a good representation, there are many things you can do. You can look at the data in a meaningful way. So here looking at fibers crossing or looking at speech. If you have a good representation, you can also denoise, which means that maybe you can estimate things with less data. And you can also build predictive systems. So what do we want to do here? We would like to learn a representation from brain waves, from brain signals. And one idea that I would like to illustrate with this picture that maybe some of you have seen is this idea of using self-supervision. So what it means is that we're going to, here in the specific example in the vision context, it's not EEG, it's just really vision. You take an image and you slice the image in small portions like this. You shuffle the portions and you try to train a deep net to recover the original of the image. And basically the system is able to say, okay, this looks like a head, so it must be above. This looks like the legs or the feet of the tiger, so it should be below. Ultimately, what it means is that there's some kind of high-level abstract concept that was learned by the network in order to solve these jigsaw puzzles. So these types of tasks that you can easily build from natural images are called, in the context of SSL, they are called pretext tasks. So you're trying to solve a pretext task, and what you hope is that if the pretext task is correct, you're going to be able to learn a representation that will be very valuable and very useful for a downstream task. And of course, the downstream stack should be of practical interest. So if you look at the history of SSL, so here there's actually a lot more work also more recently, but let's say historically started with NLP, with solving masking problems, so basically recovering the right word that was masked from the data. The jigsaw puzzle that I illustrated right here, you can also predict in which order frames are appearing in videos. And here I will come back to CPC in a minute. MoCo and SimCree are also typical impactful results that are based on SSL ideas and contrastive learning. So this has been very much examples in NLP and computer vision. No works was really pushed to our knowledge beyond these types of problems. And so the idea is, okay, what would be a good pretext task? What would make sense to look at when we study EEG? So for this, we need enough data. So I said in the talk, we need to find some way to collect enough data to learn things and do not suffer from the small n problem. So suffering from the fact that we have few observations. And it turns out there's something called polysomnography, which is a clinical exam that you can easily do everywhere in the world, for which you have reimbursement from social systems, and basically allow you to get measurements of your brain and muscle activity during your sleep. And this is useful to get some kind of diagnosis about your sleep patterns. And the benefit of this is that these types of data, because they have a clinical value, they are very often annotated by experts. So basically it means that there are some labels that we can use to validate. So there are two problems that we can do with these types of signals. The first one is a plain classification problem, or maybe you could see this as a sequence-to-sequence problem, but you have typically 8 hours of recordings, 8 hours of multivariate time series, and you summarize these 8 hours by a bunch of sequence of steps, which is called here hypnogram, where you have 5 classes for 5 states of your basically your sleep, and you see these types of cycles that appear here. So if you can see this as a classification problem, but you also have another types of tasks that you can do with the signals, which looks very much like object detection on images, which is to detect here so-called micro events, so it's like small events like sleep spindles, if you've heard this. And this is close again to a computer vision task, because you need to say when things happen and what types of signal this corresponds to. So you see this as a bounding box and defining what's the label of the bounding box. All right, so I'll spend 1 minute on explaining this downstream task before showing how SSL can be designed. So here, this is your EEG recordings, and your samples, your features is multivariate time series. Here I call X. Typically a chunk in windows of 30 seconds. And what you would like to learn is a function f hat that takes an input sample like here and outputs a stage. Are you awake? Are you in so-called rapid eye movement sleep? So basically when you dream, or are you in sleeping in stage 1, stage 2, and stage 3 would be in deep sleep, where typically memory consolidation happens. All right, so the first task that we look at is what we call relative position. And the idea is the following. If you sleep across multiple stages, it's very likely that over a window of a few minutes, you're still in the sleep stage. Okay, so the task that we designed is called, the idea is the following. You sample pairs of observations. So you sample pairs of time series. And you're going to train a deep net, typically a convolutional neural network, to classify if the pairs of samples are close in time or far in time. So it's really a binary classification problem where you've constructed from the data without any human supervision a classification task that hopefully will lead you to a representation that is meaningful. As a remark, it's very much related to the work of Apo Ivarinen on permutation contrastive learning. The other task that you can explore is it's called
Alex,
inspired.
are you taking, this is not a time series model, no? So you're not taking into consideration to do this classification, the time structure of the data, no? Or I'm confused.
No, so a window is 30 seconds, which means that the embedding, the network that learns representation works with the time series. So typically does convolutions, but we don't exploit the fact that there are chunks within a global time series. So, but still what you provide is more than one time sample. It's really a window.
Okay.
Does it make sense?
So you take advantage of the correlations in the time window, but you're not assuming that the different time windows are correlated with each other.
Think of this as there's some kind of spectral features in 30 seconds of signals. And so something that is really a time series feature that is extractable from 30 seconds of data. Okay. This you learn from your learning systems. Okay. And this representation extracted from 30 seconds, that is typically the output of like convolutional layers, will be used to classify if two chunks of 30 seconds, for example, they are closer in time than 5 minutes. Okay, did you sample the two windows of 30 seconds in less than 5 minutes, or are they like longer, like more distant than maybe 30 minutes or 1 hour or 2 hours? Okay, so you have to, you see what I mean?
Yes.
Okay.
Thank you.
So the other task so if you know the work on PCL from Apple, here is working with just neighboring samples. Here we're working with windows. That's a subtle difference. So the other task that you can use is inspired by the work of Ortetal on so-called contrastive predictive coding. So if you have a bit of background in neuroscience, that probably rings a bell. And the idea is that given some kind of representation that you've learned from the signals up to now, so let's say at a given point in time, you have a kind of a way to summarize your past, and you end up with one basically representation or one embedding value for a given past. You would like to predict what's your right future, what's the future that you are that is coming next. Okay, so intuitively, you have a batch. I'm trying to give maybe too much details, but maybe for this audience it's relevant. You have a batch in your training. Every batch is basically a sequence, and you're trying to predict what's the right future for each of your samples of your batch. Okay, so imagine that you have a batch of 30 sequences, then one future for each of them, and you want to predict which one is which one is the future of which. Okay, so it's a contrastive learning task where you want to be correct for the right future and wrong for the other. So it's like a negative, positive, contrastive task. And here, since you have multiple negative, because you have as many negative as typically your batch size in the way we do it, the loss that you optimize is called info NCE, which is again very much studied and used across different SSL tasks. Okay, so
Alex,
this is, yes.
Just a quick question. I mean, from a self-supervised technique, the method seems very sensible, but like info NCE also has relationships with like mutual information computation, these kind of things. Is it something that you can leverage in like finding some pretext task, or is this part of info NCE completely decorrelated from this?
So are you asking what's the connection between the info NCE loss and like the mutual information?
I guess
quantity?
the question I was asking is like the task of predicting a future sample seems very sensible from when you want to create a pretext task, but there is also this whole part of info NCE that's about just estimating mutual information between like a joint in a joint distribution. And is it something that you apply somehow in like or that you draw relationships to with this like pretext task finding, or is it something that you don't explore? Just as a question.
But definitely what you're capturing is the the connection, the statistical relationship between the future and its past. So there's definitely it's definitely related. But here it's like, what do you condition on? And you're conditioning on the past samples, or some kind of embedding of your past. And the way it's done here is typically fluidly with a recurrent net, where you just take the activation of, let's say, a GRU or LSTM of your past, and you just take the hidden layers of this, and this is your input vector, let's say of size whatever 100, and that summarizes, and this is the vector that allows you to predict the right future.
Okay.
So. All right, so the task that we're exploring, I'm giving you a bit of details on this to give you also an idea of what's the sample size that we're working with, because I think it's kind of related to what people can work on different types of applications. So we work with two types of downstream tasks that are both relevant for clinical context. The first one is this issue of sleep staging, and another one is pathology detection, where people get EEG on their head, and it's becoming a binary classification problem. Is the subject has a damaged brain, yes or no? Okay. To give you again a bunch of numbers, a sleep recording is typically people sleep for, let's say, 6, 7, 8 hours, and you get windows of 30 seconds, which means that in this data set where we have close to 1,000 recordings, this is the repetition, the percentage that you have in different stages. At the end of the day, you have roughly 1 million samples. And from a context of, I would say, ML in healthcare or neuroscience, that's fairly huge, at least from my perspective, on human data. And if you look at TUH, this is still on the order of a few thousands, but this is definitely a bit smaller, but clearly more than 50. Okay. Why I'm saying this is because these are types of tasks that allows you to get confidence in your results, because you have fairly big sample sizes. Okay, so what do we see with these types of pretext tasks is that the representation that we learn allows us to learn with limited set of annotations. So what you see here in this graph is that if you take very few samples, you recover the fact that the representation that you've learned, when you feed it into, let's say, a multinomial logistic regression in the context of PC18, so with 5 classes, or binary logistic regression here in TUH, you manage to get performance much higher than using purely just supervision by using these types of pretext tasks. Now, there's more interest in these types of work, in these types of application. It is, what do we learn? And so here, this is just a UMAP embedding of the embeddings that are extracted for each of the 30-second windows. So one dot here is 30 seconds windows that is embedded in dimension 100. And then we do a UMAP nonlinear dimensional reduction in dimension 2. Okay, and then we color code every dot with the annotated sleep stage. Okay. So what you see here, so again, these sleep stages, they are not used to learn the position of the dot, they are just used to color the dots. Okay. So what you see here is that by using these types of pretext tasks, you learn some kind of latent structure in the data, where here all of these dots, they are basically extracted during when subjects are awake. Whereas here, when you go closer to this other edge, where you're here in dark green, you are in deep sleep. So what you see is that basically these kind of banana that is color coded corresponds to kind of a continuous stage in your sleep patterns, which is discretized in 5 classes, just because humans that are annotating this data, they are basically limited by, I mean, they're not going to annotate continuously over 15 stages. Okay, and the other thing that we obtain on these types of problems and these types of data with these types of tools is here some kind of latent factors that we recover that is related to age. So here now we color the dots, not with the sleep state, but with the age of the subjects. And here you see that the people here at this extreme, here they are the young people, okay? And here at the inner part, they are the older people. So it's as if from a statistical point of view, you have some kind of latent structure, okay? So you're learning a representation where you have certain factors of variation that are expressed in a meaningful way, and typically here age. Okay, so there are many questions that you can ask also in terms of statistics about, okay, can you disentangle these types of representation? There are many problems that can emerge from this, and I'd be happy to discuss about this later if you want. Okay, so and
Alex,
we can
and
also
how
yes.
does this representation compares with PCA, Disney, factor analysis? So is this structure easy to extract, or is it something unique from your from SSL?
So if I say UMAP versus Disney, I think you would get very comparable results if you start from the embedding, to be honest. Now if you start from the raw signals, there's no way you have the same types of representation to do the same thing with just raw signals. You need to extract some features. The features of this data, which is maybe a bit implicit in my presentation, is that some aspects are related to like micro events. Okay, for example, you are in stage 2 when you have these types of like burst of spindles that I mentioned before. So there's a bunch of like so-called microstructure, or like, for example, if you're in deep sleep, you tend to have very slow waves, so some kind of your power spectrum that is focused on the slow frequencies. So there's a bunch of like features that you can handcraft to kind of discriminate these types of classes. But here, I guess the pitch is that you can do it completely automatically from the data, right? And if you do a linear, like if you do just a PCA, then you don't see the structure, at least from the embedding that we obtained. And if you do it with handcrafted features, then the question is, what do you choose? Okay, how do you select these things? Because here, what is neat here is that the pretext task allows you to learn in a completely supervised way, which means that you can do model selection, you can optimize your network architecture based on your pretext task. So there's from a statistical point of view, it's very convenient because you're in a kind of safe world. Where
I think, Alex, it's fantastic that that you're learning these features automatically, you know, because many people do, let's say, they do spectral features, they do, you know, it's an art, the issue of how to select the features, you know, and it's very nice, very interesting that you're extracting this automatically, you know.
Yeah, and I think there's so many issues.
Now the question is how this structure would compare if you take, for example, spectral features. So how important are the features that you're learning compared to the structures, to the features, you know, that you can learn just by taking, let's say, the Fourier power in a given window. So the important thing is how rich are the features that you're learning compared to the features that you can learn with manually, no?
That's a fair point. I don't have any picture to illustrate any answer, but I get I think it's a fair question, to be honest. Yes. But I don't have any backup slides to answer to this, so I cannot really tell you. Well, I mean, what we see is that in order to what is maybe one way to answer is that if you don't manage to solve the pretext task, or if you don't do a good job at the pretext step, you don't get this. Okay, so the fact that you have a good score on the pretext allows you to obtain clear embeddings like this. It's not completely answering.
No, what I'm wondering is what are your networks? What features are your networks learning? No, because in that case you can inform the people that are building features manually. Hey, this is what you should be building if you want to get good embeddings that have good predictive power, for example. No, so can you comment about what are the spectral characteristics of the features that you're learning? Well, a temporal
so I don't have any slides here, but we worked on we did some kind of ablation study in the supervised case in the previous works, and basically bandpass filtering or masking certain frequencies in the network and see how it affects the score. So just to see some kind of like permutations, sensitivity analysis, or some kind of parameter sensitivity analysis to see how much the spectral content of the signals is affecting where you end up in the embedding. So I think it's one way at least to partially answer this.
Okay, thank you.
So the other result that I would like to illustrate here, and I guess this talk is also maybe to show you that there's a lot of interesting problems to look at on these types of data. So what you see here is now the embedding, so the UMAP embedding that we get with the TOH dataset. So this is binary classification. Is it a healthy brain or kind of a damaged brain? And what you see is that the embedding has these types of smaller islands here, and you may ask yourself, okay, why do I have these types of islands? And these islands are very much related. So these data are basically collected for a very long time period in one hospital, and over the years and over the time, basically the acquisition devices has changed, and the input distribution has changed. Okay, so what you see here is that the representation or the embedding that you learn is kind of sensitive to what you would call maybe the domain in a statistical sense. Okay, what was the device or the cohort from which the data was collected? Okay, is there some kind of non-stationarity in the data that was due to a change of device? Okay, does it make sense? So here, there's two things I would like to illustrate. The fact that you see some kind of gradient between. So there's a way to classify. Probably it's not linearly doable in 2D, but being dimension 100 is doable. But you also see that you have in your data some intrinsic, basically subclusters that get revealed to you with these types of analysis. And these clusters you can kind of analyze them post hoc. And this is what we did, showing that these clusters are related to changes in acquisitions and related to when the data was acquired, which is, I guess, a very classical problem in types of healthcare data. Make sense? Okay. All right, I'm not going to comment too much here, and I'd like to maybe jump to the second work in the team that I would like to illustrate this afternoon. Okay, so this is, I'm switching gears here and switching topic with the work of Charlotte Cocheteau, who's doing a PhD with me and Jean-René King, where we try to kind of bridge the gap between brain and machine in the field of language processing. And the idea of what we're doing is can be illustrated with works from other people, which is the work of Jim DiCarlo in his lab at MIT. So here, this is probably in the case of context of vision. Okay, so you want to relate the activations of a deep net trained to work on natural images with neurons that are related, that are in the human brain, or it's the monkey brain, because they are invasive recordings. Okay, and what they were trying to reveal is how much certain regions of the brain, typically IT, can be mapped to certain neurons in the deep net, and what basically, what did we learn? What does it learn, and what does it correspond to? Okay, so what they propose, and now it's very much used in the literature, that they're looking at so-called brain score. The brain score is how much representation from an ML system or AI system is appearing to be brain-like. Okay, and what they show in this paper is that there is some neurons, okay, some part of the neural network that is trained on these natural images that has an excellent correlation with neurons in IT. Okay, so just showing you this from just pure empirical data, you see, okay, so if these two lines, they are very correlated, so this suggests that this neuron is very much behaving, at least in terms of feature extractor, with what the network is doing. All right, so this is just the methodology in general of this line of work. And so you can ask yourself, okay, what can you do now when you work on language tasks? And one of the questions that people have been asking on language is, what is the hierarchy of language processing, because you parse phonemes, then you parse words, then you assemble these words to obtain sentences. These sentences, they are assembled together to produce paragraphs and stories. And okay, so you have these types of hierarchy. And so the way people have addressed this without any AI, just using purely what I here call model free is, so here's the work of Lerner et al., where what they're doing is that they have a number of subjects listening to natural stories. So typically they spend 7 minutes in an MRI listening to stories, and you collect your brain signals for each of the stories, and they do something extremely basic from a statistical point of view. They look at what they call inter-subject correlation. Okay, so how much is the brain of one subject correlates with the average response across all the population? Okay. So if all of the subjects correlate with the average, by averaging, they assume that they extract basically the common patterns of the brain response to these stories. They can say how much a region is engaged in the input stimuli. And the innovation in this work is to scramble the inputs. Okay, so either they give you the regular story, like once upon a time, Merlin met Arthur, blah, blah, blah. Or they shuffle the sentences. Basically, they shuffle the sentences to break the paragraphs. Okay, so they destroy the story, the high-level features by scrambling the sentence. And so here, scrambling at a lower level, and then at the end, they scramble words, where now they take all the words and they completely shuffle the words. And they see, okay, how much now is the brain still responding to this kind of scrambled input? Okay, and by doing this, what they obtain is something like this. And this is showing you what? It's showing in red all the regions that are still very much active when you're still at the level of acoustic features. So you find the auditory cortex. And here, when you start to scramble sentences or paragraphs, you kind of reach out to higher level parts of the brain, which are still very much involved, or at least specifically still involved when you work with paragraph level, so really high level features or high level aspects of language. Okay, so by using these types of techniques, they can kind of map, okay, what part of the brain is processing words, what part of the brain assemble words, what part of the brain is involved in like big picture stories at the level of paragraphs, and they do this in a completely model-free way. So what we did last year with Charlotte is the following. So we're going to take a pre-trained network, so typically GPT-2, and from the different layers that we extract from the transformer. Okay, so here GPT-2 has 12 layers. So we have the representation that is extracted from the raw text. So there's no brain here, and we're trying to see how much this representation will correlate. Okay, at least linear. It can be, there's actually a linear mapping that you learn. Okay, so it's not really a one-to-one correlation. You allow yourself to estimate a linear model that goes from the transformer activations to the brain signals. Okay. All right, so this is kind of the general idea, and typically you have all the voxels in the brain, so typically 40,000 voxels, and here a number of recordings is obviously less than the number of words, because you have one brain volume, let's say every 2 or 3 seconds, whereas the number of words, maybe you have 2 or 3 words per second. Okay. All right. So this being said, we can compare the model-free approach with some kind of GPT-2 extracted features in order to see, okay, can we use these types of NLP systems trained from huge cohorts on the web to answer these types of clinical or cognitive neuroscience questions of extracting the hierarchy? And so how do we do this? The idea is the following. We're going to do the same types of scrambling. Okay, so we're going to destroy the structure of the text that is fed to GPT-2 at different levels. Okay, either we shuffle all the words and we extract the GPT-2 features, okay, or we shuffle the sentences and we extract the GPT-2 features, or we scramble the paragraphs and we extract the features. And what we are going to look at is how much these features extracted from GPT-2 with the scrambled input kind of correlates with the brain. Okay, that makes sense?
Yes.
Okay. So this allows you to run these types of acquisition, run these types of tests with only one subject. Okay, so this is really taking one, like basically replicating some kind of cognitive experiment with one subject. We have the subject data for the original data sets. Okay, not with all the scrambled acquisitions, but we see how much do we affect the mapping or the linear mapping when the input is scrambled. Okay, so maybe just to repeat, in this particular type of analysis, we don't need to collect 5 types of conditions. Okay, we just collect the real stories, and we're going to see how much the scrambling is deteriorating the performance.
Mm-hmm.
So here, this is the types of result that they obtain with all of the data. Okay, this is now what we obtained with our kind of what we call model-based using GPT-2. And here, historically, they did it with 7 subjects. This group released, this part of this group released a lot more data, including the same 7 minutes of stories. So this is what we obtained with 75 subjects, and they also have an entire, a bigger cohort with more stories than these ones. And what you see with these types of model-based approach, you can also map these types of hierarchies with very strong statistical confidence, significance. All right, so this is one type of
Alex, and what is the difference between what you found and the previous study in terms of areas? No, did you find some areas that people didn't find before? You have better resolution?
So I guess this question should be answered to my co-authors who are more clinical and cognitive, like cognitive neuroscientists than myself. From my engineer and CS point of view, you do recover expected regions. Okay, the question is, when you look in close details, how much do it differ? I agree, that's a very relevant question, So
I wonder, what is the transformer bringing to experimentalists? No, what are we gaining?
So I guess I see this as a way to ask novel questions, because now you have a system that you can play with to extract representation that allow you to test new hypotheses. And maybe I can illustrate it with the next slides, and I'll come back to your question in a minute, just to show you what we can do with these types of techniques. So what we do here is trying to use these types of ideas to disentangle syntax and semantics. Okay? And the idea is the following. Okay, so we have a way to produce features from text using GPT-2. And what we can do is perturb the input signals in the sense that we're going to keep something that is syntactically equivalent. Okay, so for example, I will go from not very happy to dimly so true or widely right good. Okay, so these are all syntactically equivalent text. Okay, and if we extract the activations for all of these syntactically equivalent input stimuli, and we extract the GPT-2 activations from all of these, let's say, equivalent sentences, okay, what we are obtaining is some kind of representation that we claim to be the syntactic representation of the input. Okay, so I give you a text, I replace all the word to keep something that is syntactically equivalent, and that gives me a GPT-2 representation that is averaging out, or like averaging and basically canceling everything that is not related to syntax. Okay, so the claim is that by using these types of processes, we are able to extract this purely syntactic representation. And then what we're going to do is compare our ability to predict brain signals from purely syntactic components to the original representation that will contain typically the syntax plus the semantic. Okay, So let me make it clear here. Okay, so we have from the NLP network, we have the lexical level. So basically just the word embedding. Okay, just see this as word to vec if you want. And then we have all the feature extractions from the transformer. Okay, so by doing this averaging trick, by taking some syntactically equivalent input sequences, we can extract an embedding that is purely syntactic. And what we can then look at is what we call the brain score of the purely lexical features, the full features, or what is just restricted to syntax. Okay. And so by just looking at what is everything minus the syntax, we call this the semantic part of the embedding. Okay. And then we can compare our scores when we take the full representation versus the purely syntactic. Okay, so by doing these types of manipulation of the inputs, we kind of orthogonalize the text with respect to syntax and obtain some maps, which here are the maps of brain scores. What you see here is that the semantics involves basically Broca's area and more frontal regions, whereas syntax is more related to temporal areas. Okay. So I'm not going to comment again too much into specific brain areas, but what this shows you is that these types of tools that we had used with the Eichenberg paper, replicating retinotopy results at that time, we can use the model extracted from vision or NLP task to test things with less data and accessing to less data, and maybe also doing some experiments and testing some hypotheses for data that was not specifically collected for. All right. I don't know how I'm going with time, but I wanted to talk a bit more on the last part of the work, which is, I'd say, more like statistics textbook, maybe for a wider audience in this crowd today. So if you give me a few more minutes, I would like to maybe mention the work of Hugo that is related to using ICA and multi-view to extract interesting features from multi-subjects and recordings from multiple subjects attending to natural stimuli. All right, so in order for you to understand the relevance of this, I'm going to illustrate this with basically what is classical neuroscience or cognitive neuroscience experiments. What you do is that you have a control experiment where people typically press buttons, they watch a checkerboard, they read words on the screen, or they listen to things. Okay, and all these very discrete conditions that basically the human experimenter needs to think. Okay, needs to basically discretize. Okay, button press, right finger, left motor, left finger, and everything gets embedded into here a matrix A that is typically a design matrix. Okay, and what people are trying to learn then is how much for each of the voxels is the voxel involved in each of the conditions. Okay, so you have by solving this kind of linear regression where F, forget about F, this is related to the hemodynamic response function in fMRI. See this as just identity. This is basically a plain least square, okay, where each voxel is going to be, okay, this voxel is more left index, this voxel is more right index, etc. Okay, so you need to discretize upfront your conditions. What I started to emerge over the last maybe 10 to 15 years is to try to use more naturalistic stimuli. Okay, and the idea is that you have people typically listening to stories or watching movies, and if you do this, basically you work in kind of an infinite feature space. Okay, so how do you describe a specific frame of an image? Can you maybe say a specific action or specific, is there a cat in the image? Okay, this maybe requires you to have some kind of discrete dictionaries of what the movie contains, which can be extremely cumbersome and potentially. So the idea of this work is to frame this problem in a statistical sense, where here I assume that I don't know the contrast, I don't know the conditions, they're just movies. But what I can do is use the fact that I have many subjects that are listening or watching the same movie. And so you go from this model where you have use explicitly the ICA types of notation where X equal AS, X is what you measure, A is the unknown, so here is the known mixing matrix, and here's the sources. If you're in the context of ICA, the mixing would not be known. But here what I'm saying is that I have multiple data sets. I've got multiple data sets for a bunch of subjects. All the subjects, they are mixed in a slightly different way. So the mixing depends on the subject, but the sources are going to be the same. Okay, so if I write this from a statistical point of view, I assume that my data here is just a linear mixing times some sources that do not depend on the subject, does not depend on which person is in the scanner. I assume that every brain will basically respond and produce the same waveform when they watch whatever movie, okay? And I'm going to try to estimate the mixing and the shared sources from the data, okay? And for this, basically borrowing ideas from old school ICA is to assume that all the sources are independent. So what it means is that the density of the vector of sources can be factorized into the density of each of the entries in the sources X. Okay, so D is going to be the density of each of the sources that I'm going to assume to be the same. Okay, and here, a subtlety here is that contrary to maybe what most people would do, we don't put the sources, the noise outside. Basically, we don't say that X is AS plus the noise. We put the noise inside. And by doing this, it allows us to have a very convenient closed form likelihood of the model. Okay, so if you just write the likelihood of the in this specific context, what you're trying to recover is the mixing matrix. Okay, so the mixing will be recovered through its inverse that we're going to call W. So it's W is the unmixing matrix. Okay, so applying W to X gives you S. And just writing the likelihood ends up being parameterized by these W that you want to recover. If I give you the W's, then you're done. Okay. It's not super important I mean, not too hard to see why it looks like this, but let's assume that we skip a bit of the details. Okay, so this, you can see this some kind of how much the sources that you estimate for each subject, they map the average. Okay, so this quantity should be small, which means that all subjects mapped to source space should be close to the average source. This is just the Jacobian of the determinant to go from the linear due to the linear unmixing. And this is just your source densities for each of the sources. All right. The gist of this work is that by basically maximizing the likelihood of the data or minimizing the negative log likelihood, we have a problem that we can solve efficiently. Okay. So the likelihood, if I try to convey some maybe interesting, more general ideas in this slide, is that what people have used to optimize these types of problems in the field of ICA for the last maybe 20 or 25 years is to use so-called relative gradients. They are not, it's gradient descent, where the change that you're going to apply to your parameters at every step is a multiplicative correction. Okay, so maybe it's a bit original for you, but really the update rule is saying that the previous iterate of W gets corrected by a matrix in a multiplicative way, where the matrix is just identity plus some kind of tiny correction. Okay, so with this idea in mind, okay, so you do a tiny correction rather than just doing a gradient descent, what would be Wi minus the gradient step. You can write the Taylor expansion of your likelihood where you have a tiny perturbation of your W's. Okay, you're gonna get a first order term that depends on the perturbation, a second order term, and this linear term gives you the so-called relative gradient, and the second order term will give you a relative hash. Okay, so it's like a Taylor expansion where the perturbation is multiplicative and so-called relative. Okay. Once you write this, it turns out that the update rule is nothing more than a Newton step in the relative sense. Okay, which means that the gradient or the direction that you use to correct is a relative gradient multiplied by the inverse of the Hessian. So this is really a Newton step, but again, a Newton step with a relative perturbation. Okay, so a Newton step would otherwise, Wi is equal to Wi minus some step size times this. Okay, so here it's inside the band. What we showed in this work is that both the gradient and the Hessian is sparse, which means that this Hessian, okay, is huge. Each of the Hessian is number of sources, number of sources, number of sources, number of sources, because what you're trying to recover is as many matrices of size P by P times the number of subjects, which means that the Hessian basically is the quadratic dimension size, which means that you go from P squared to P power 4. Okay, so your Hessian is huge. And so what we show is that we can approximate this Hessian in a cheap way and solve this in a very efficient way. Okay, so maybe there's one thing to remember is this idea of using relative changes and doing matrix approximation of the Hessian to do things in a more efficient way. All right. And so what we also showed in this line of work is theoretically that we have a so-called identifiability. And what it means in this literature of ICA, it means that if I've got two sets of matrices AI and AI prime that satisfy this relationship, which means that they can go from some shared sources to the data with some additive Gaussian perturbations, okay? So if I have two matrices that satisfy this, then there must be a permutation and a scaled a matrix P that you can just see as a permutation matrix with some arbitrary scaling that relates A and A prime. Okay. So it means that you cannot recover the order of sources and you cannot recover the scale of the sources. Okay, so what this result shows you is that up to permutation and scaling, these types of model is identifiable and we have a fast algorithm to do it. Let me maybe speed up a bit. And so we apply this to both MEG and fMRI. So in the context of MEG, this is a control experiment where here this is a fake plastic head, where at each of these black regions, we have a candidate source that maps to the sensors here positioned on the blue regions. And each of the sensors, they can be arbitrarily activated. So we activate them with exactly the same waveform. So we have a shared source, but since they are positioned in different places, they are mixed in a slightly different way. So this is really empirical data, so real data with a plastic head, but still really recorded data in real life, where this model really holds perfectly. Okay, and what we see is that this multi-view ICA model gives you a very good estimate of the shared source, even if you have a very few epochs. So epochs here is to be understood not in the deep learning context, but more trials or repetitions of the experiment. And so this is a good way to validate, because here we know the truth. We can also do this on real energy signals, where here applying this to this empirical data set. So again, MEGs is 200 subjects. We can recover some sources that shows you kind of a wave of activations that you can remap into brain space. Okay, and so these are the kind of shared sources that you recover from MEG. So here there's no ground truth. Okay, the only thing that you can say is that you have a sequence of regions and you have things that are kind of maybe evolving over the cortex. And what you can do still on fMRI, so using these types of techniques, I think it's super important to ask yourself when you work with these types of data, how do you validate? Because when you work on NLP on vision, typically you can look at the results and this will tell you if you've done a good job. When you work with these types of brain signals, you need to scratch your head a bit to know, okay, how do you quantify the performance of your technique? And so here, the technique to validate and to quantify the performance is called time segment matching, where you're going to take n-1 subjects. From this n-1 subjects, you estimate the shared source. Okay, so each subject, you have an unmixing, you get a source for each of them, you average them, that gives you the shared source. And then you try to see, okay, if this is the shared source, can you find over the entire movie to which segment of the movie this corresponds to? So here we take 9 frames, so 9 frames at maybe 2 seconds per frame, roughly 20 seconds of data. And here we're trying to see, okay, if I sample randomly 20 seconds of recordings from my movie of typically people watching Riders of the Lost Arch from Indiana Jones. Okay, so you have the Indiana Jones movie, you have an entire movie. And from 20 seconds of data, we recover the shared sources and we tell you, okay, can you predict to me which 20 seconds of the movie this corresponds to? So since the 20 seconds over the entire movie is pretty much nothing, okay, your chance level is pretty much 0. And what you find is that with these types of techniques, okay, so here it's very obvious on this data set, that you can really nicely identify which 20 seconds of the movie the person was actually watching, okay, which I think is pretty impressive. All right, with this, I will try to maybe conclude by saying that if you want to try these types of techniques, there's a number of code that is available online. Maybe then also get you started with these types of data, both for sleep EEG, so including the self-supervised task that I mentioned before. We've worked also with Hugo on this NV-Learn package, which allows you to do multi-view learning. And now maybe just to open a bit the discussion, there an interesting question that we ask ourselves in the team right now. The first one is, what is the optimal noise distribution to use in contrastive learning? So we have this preprint, recent preprint with Omar Shoab and Apo on trying to look at in NCE, so in the NCE estimation framework, what is the best noise distribution to use as contrast? And this is work that's still basically the PhD work of Omar. And now there's another line of work that we're doing, which is at the interface with, let's say, meta-learning, where we're trying to learn augmentation policies for these types of signals. If you look at SSL tasks in vision, like SimClear or others, they are very much based on augmentations. Basically, by augmenting an image, you augment the data by preserving the labels, okay? So you augment in a way that preserves the labels, and then you use this as positive pairs versus two images that have nothing to do with each other, that would be negative pairs, okay? So these augmentations, they're everywhere in SSL on computer vision. And what we're trying to do here with Cedric Romer, who is the postdoc in the team, which is, what are good augmentation, and can we have techniques that allow us to learn optimal augmentation policies for arbitrary data, but typically data which are not vision and not computer vision problems. And I guess that's it. And thank you very much for attending, for your questions, and I'll be happy to take more questions if you have any. Thank you very much.